Good morning, students. Welcome to Complex Analysis Live Lectures. In this class, we discuss Maximum Modulus Principle for analytic functions. Okay. So, to start with, we'll start with a lemma which will be used to prove this Maximum Modulus Principle. Okay. So, the idea is if you have an analytic function which is non constant in a given domain D, then it cannot have a maximum value inside that D. Whatever, if at all it exists on the boundary of D. Okay, that is the main idea. For that, we'll start with a lemma. What it says is that suppose that mod f of z is less than or equal to mod f of z naught uh, for at each point z in some you can call it in some epsilon neighborhood of z naught, okay, in which f is analytic. Okay, so you have a neighborhood mod z minus z naught is less than epsilon. Okay, right, so this epsilon neighborhood of z naught means mod z minus z naught is less than epsilon. Okay, and in which f is analytic, then this f has to be a constant function. Okay, then f of z is a constant function. You can say taking this value, taking the f of z naught. Okay, so that throughout the neighborhood mod z minus z naught is less than epsilon. Okay, so this is the lemma, which what it says is that if at all you have a neighborhood of z naught, epsilon neighborhood of z naught, such that if mod f of z naught is the maximum value in that neighborhood, and if f is analytic in that neighborhood, then f has to be only possibility for f is constant function, of course, which takes f of z naught, because f of z naught it is there inside already. Okay, fine. uh we'll prove this. So let me draw this picture first. What we have here is we have a z naught. Okay, then we have a neighborhood. So let me draw a little bigger. So assume that whatever I am drawing, okay, so it is a neighborhood. That means uh, assume it has equal sides and okay. So what we have here, this is our epsilon. Okay, fine. Then in this neighborhood, what we have assumed that mod f of z is less than or equal to mod f of z naught, and f is analytic inside this. Okay, so we have f which is analytic here, and we want to show that f of z is equal to f of z naught throughout this. That means we want to show that f of z is constant. Okay, so how we'll do is we'll take an arbitrary point, say suppose z1, okay, which is different from z naught. Okay, then we will take the distance of z naught and z1. Okay, you can call it some rho, whatever it is. Suppose if this distance, whatever we are having, if this distance is rho, then what we do is, because this is z1, so we will take a circle. Okay, we will take a circle around this z naught, okay, of radius exactly this rho, right? Then z naught is an interior point to that, and f is analytic, so we can apply Cauchy integral formula. We get the value of f of z naught. Okay, and finally we will show that f of z naught is same as f of z1, and since z1 is arbitrary, you can move this z1 anywhere, so we get that f of z naught is constant throughout this neighborhood. That is the idea. Okay, so let me draw that. So we will take a neighborhood. Okay, this, this is a neighborhood. Sorry, not neighborhood. This is the C row. We can call it C row. Okay, the positively oriented circle centered at Z naught. Okay, so we'll start writing the proof. So let Z1 be a point, okay, in the neighborhood different from Z0. Okay, we can call it let Z1, the distance between Z1 and Z0 is rho, right? Now let C rho be the positively oriented circle, okay, mod Z minus Z0 is equal to rho. Okay, so if you have any point Z here, if you have any Z here, the distance from this to Z0 is rho. Okay, now since f is analytic on this entire neighborhood, so in particular f is analytic inside and on the curve C rho. Okay, f is analytic inside and on the points of this circle C. Okay, and Z naught, okay, is interior to this 0, right? Therefore, by Cauchy integral formula, what we have is the value of f of Z naught is 1 by 2 pi I times f of Z upon integration of f of Z minus f of Z upon Z minus Z naught dz over 0. Okay, right. Now what we do is we'll just like when we contour integral how we are simplified, so we'll try to simplify this. So what is the our 0 is mod Z minus Z naught is equal to rho, right? This implies we can write Z in terms of polar one, that means parameterization. So this is same as Z is equal to Z naught plus rho into e power I theta. Okay, that means you can write here Z minus Z naught is rho into e power I theta. That is same as this, where theta is from 0 to 2 pi. Okay, because it is a circle, right? Fine. Therefore, what is this will become f of Z is f of Z naught plus f of Z naught plus rho into e power I theta, right? And this implies what will be dz? Dz, this is 0, so rho I e power I theta d theta. So therefore, f of Z naught is 1 by 2 pi I times integration. Now it will become 0 to 2 pi because theta is from 0 to 2 pi. F of Z, we can write this as f of Z plus, f of Z naught plus rho into e power I theta. This is here. Rho into e power I theta upon what is Z minus Z naught, that is our this rho into e power I theta, rho into e power I theta into dz. What is our dz is rho I e power I theta d theta. Okay, so what are all terms get cancelled? This rho e power I theta, here I will get cancelled. So what is remaining here is 1 by 2 pi is of integration of f of Z naught plus rho e power I theta d theta from 0 to 2 pi. Okay, f of Z naught, right? Remember this Z naught plus rho times e power I theta is nothing but any point here. It may be, it is a Z1, not only Z1, it is any point here. Okay, so we got that f of Z naught is 1 by 2 pi times integration of this. Okay, on the other hand, this implies mod f of Z naught is less than or equal to 1 by 2 pi integration of 0 to 2 pi mod f of Z naught plus rho into e power I theta because modulus of the integration is less than or equal to integration of the modulus, which we already proved, right? We can consider this as inequality 1. Now, what can you say about the other way? Also, where is this point z naught plus rho into e power I theta? This z naught into, let me draw this. So this is the any point which is z naught plus rho into e power I theta. So this point is z naught plus rho into e power I theta because their distance is exactly rho, right? Now, our given condition is that for every point in that neighborhood, mod f of z is less than or equal to modulus of f of z naught. So in particular for these points also this is true, right? So by assumption, also by assumption, that means by given condition, mod f of z naught plus rho into e power I theta is less than or equal to mod f of z naught. Okay, what is the reason? Because this z naught plus rho e I theta is a part in that neighborhood. It is actually a point on that C row, right? So if this is the case, then if you take the integration and we will try to simplify and we get another inequality. From that inequality, you will see that these two are actually equal. Okay. So how we'll do that? This implies integration of 0 to 2 pi. Okay. Modulus of f of z naught plus rho into e power I theta. Okay. This is less than or equal to less than or equal to with respect to d theta. Okay, is less than or equal to integration 0 to 2 pi mod f of z naught d theta. Okay, but remember this right hand side, this is whatever we have here, it is independent of theta, so that will come outside, and what is here is will be 2 pi times this one. Okay, so this implies 0 to 2 pi mod f of z naught plus rho into e power I theta. Okay, d theta is less than or equal to 2 pi times mod of f of z. Okay, so if you bring this 2 pi here, the same as 1 by 2 pi times integration mod f of z naught plus rho into e power I theta d theta. This is less than or equal to modulus of f of z naught, right? If you consider this as inequality 2, now if you see inequality 1 and 2, what we have here is exactly the same. So therefore from 1 and 2, what we have here is mod f of z naught. This value is equal to 1 by 2 pi times integration of 0 to 2 pi mod f of z naught plus rho into e power I theta d theta. Okay, and what we do is this also we can write in terms of integration, just like how we did here, right? So this is same as 1 by 2 pi integration of mod f of z naught d theta from 0 to 2 pi, because this integration is actually 2 pi times mod f of z naught, so 2 pi will get cancelled. This is same as this. That means if I take here, okay, so this value is 0, right? This value is 0, but if you take this integrand inside, 1 by 2 pi times integration 0 to 2 pi modulus of f of z naught, okay, minus modulus of f of z naught plus rho into e power I theta, this entire thing into d theta. This is equal to 0. Now remember, this whatever you are having here, mod f of z naught, that is the maximum value, right? So this whatever we are having here, so mod or since sorry, since modulus of f of z naught minus or is greater than or equal to modulus of f of z naught plus rho into e power I theta, this implies the this mod f of z naught minus f of z naught plus rho into e power I theta, this is greater than or equal to 0, right? So you have an integrand which is continuous and non-negative, okay, whose integral is equal to 0. Okay, so by real integration, whatever we know from calculus, if you have a, this means this integrand has to be equal to 0. Therefore, mod f of z naught is equal to mod f of z naught plus rho into e power I theta. What we have used here, then if f is a real valued function, f greater than or equal to 0, okay, such that integration of f is equal to 0, that means f has to be equal to 0. Okay, so if you have a, right, this one, whatever we are having here, it is non-zero and whose integration is equal to 0, that means that f has to be 0, whatever we are having, that integrand should be 0, right? So that what we have proved is that this for mod f of z naught, so in particular this z naught you can take, right, this is a z, any point, therefore mod f of z naught is equal to modulus of f of z, okay, for every z belongs to this C row, because this z is precise, z naught plus rho e I theta is nothing but the precisely a point, any point on this C row, right? So we have, what we have just now proved is that f of z naught is equal to f of any value on this one, right? Now since z1 which we have taken is any arbitrary point different from z naught, okay, now what I can do, I can take this z in place of this z1, I can take somewhere else, then I can consider 0, okay. So I can vary z1 and I can show that take the circle passing through that z1 with center z0, then at all those points f of z is actually equal to f of z0. So therefore f of z is equal to f of z0 here. At present we are talking about modulus of f of z0, okay. So far what we have proved is that mod f of z0 is equal to mod f of z for all z belongs to C, right? This in particular, but since z1, okay, is arbitrary point, okay, in the neighborhood mod z minus z0 is less than epsilon, we get that. That means whenever you change z1 you will get another circle, at all the points on that circle this value is equal, so we get that mod f of z0 is equal to mod f of z for all z in this neighborhood, mod z minus z0 less than epsilon, okay. Now that means what we have shown is that this implies we proved that mod f of z is actually is constant in the neighborhood mod z minus z naught is less than epsilon. Remember f is analytic here such that modulus of f of z is constant. So the result which we have proved earlier, that if you have an analytic function such that the absolute value, okay, is constant, then that function has to be constant, okay. uh, since f is analytic in this mod z minus z naught is less than epsilon and mod f of z, okay, is constant. So what we get is we get f of z is also constant throughout this neighborhood mod z minus z naught is less than epsilon, okay. And not only this is constant, this f of z value should be equal to f of z naught, because modulus of f of z is equal to modulus of f of z naught for every z in it. So in particular this f of z is not only constant, it has to be equal to f of z naught, okay, in throughout the neighborhood mod z minus z naught is less than. That proves the lemma, okay, that if at all an analytic function in a neighborhood has maximum value f of z naught in that neighborhood, then the only possibility for that analytic function is constant. Now we are ready to prove the maximum modulus principle. So let me state the maximum modulus principle theorem, which is called as maximum modulus principle. So what it says is that if a function f is analytic, okay, in a given domain D, then it cannot have a maximum value in that domain, okay. So that is the statement which says that So if the statement is, if f is analytic and non-constant, okay, non-constant in a given domain D, in a domain D, then then the maximum value, that means mod f of z, okay, has, this function has no maximum value, has no maximum value in this D. D is a domain, okay. That means there is no z naught in D such that mod f of z is less than or equal to mod f of z naught for every, so that is, there does not exist any z naught in D such that mod f of z is less than or equal to mod f of z naught. Okay, fine. The proof, we will prove this by contradiction. Okay, because we want to show that there is no point z naught satisfying this condition. Okay, so proof, will prove by contradiction. That means, so that means, suppose there exists a point z naught in the given domain D such that mod f of z is less than or equal to mod f of z naught, okay, for all z in that domain D. Then somehow we should get a contradiction to given one. Either it means we will, because f is analytic, so we will try to prove that f is constant by using previous result. That is the idea. So we will somehow prove that f is constant. How we will prove this f is constant is, the approach we do here is z naught is there. Then we will take, so let p belongs to D be any arbitrary point, okay. Then we will show that f of this z naught, f of z naught is, and is same as f of this p evaluated at p, okay. Then what we will see is, because p is arbitrary, so we get that f is constant, which is a contradiction because it is a non-constant function, okay. Now we have a z naught and we have a D, and D is a domain, so it is connected. So therefore there exists a polygonal line from z naught to p, okay. Such type of result we have already discussed when we discussed about uniquely determined analytic functions. That means this z naught, how we will reach from z naught to p via z naught z1 up to zk minus 1, then taking the neighborhoods and so on, right? So let me take that picture again, and the process is same. You can go back and see that result once again. Yeah, this is the picture which we are talking about. So this is the z naught, okay. Here we have z naught, and here we have our p, which is an arbitrary point. And you can assume that, suppose this is our given domain D. Of course, when you write domain, make sure that we have dot, that means boundary is not there, okay. So whatever I am writing here, just make sure that this is our domain D, okay, with dotted lines, that means entire thing, right? Then what are all we required is that we want D is the shortest distance from this point of L to this boundary of this D, okay. Let me write that point here. So let, it is our D, D be the shortest distance from points on L to the boundary of D. That means if you take any point on this point L, then if you measure the distance to that boundary, that distance is greater than or equal to D, because D is the smallest distance possible, okay. Then we'll consider with that we can have a sequence of points, z naught is already there, so z1 z2, we can select z1 z2 and so on, zn minus 1 and zn where Zn is equal to P in such a way that this distance, so what we can write here is we can choose Z0, Z1 up to Zn, which is equal to P, such that the distance between each Zk minus Z or Zk plus 1 minus Zk, whatever you can write here, Zk or Zk minus Zk minus 1 is strictly less than D. This is always possible, okay? Because Z0 is given, so you on this line, polygonal line, you find a point whose distance is, say for example, D by 2, right? So then this distance is less than D, okay? This is true for all k from 1 to up to n, okay? This one. And not only that, we can also select now the neighborhoods and neighborhoods. So we can select not only points and neighborhoods n0, n1 up to nn, okay, such that again what is there, the whose center n0, such that center of say nk is, center of this nk is zk, center of nk is zk, and we can observe that the distance between this z0 and z1 is less than d, and whatever we are having and of radius, so each one is of radius d, okay? So each neighborhood is of radius d and center at zk, okay? Then this one, whatever we are having, this is the distance less than this is exactly d, but mod z minus z0 is less than d, so therefore z1 belongs to n0. Similarly, z2 belongs to n1 and so on, okay? So what we get, center of such that, and this zk plus 1, if you take, this belongs to nk for all k, okay? That means z1 belongs to n0, z2 belongs to n1 and so on, okay? That is the meaning of it, right? Fine. So with this information, now consider n0. Now consider n0, and what is our supposition? Our supposition is that f of z is less than or equal to f of z0 for all z belongs to D. Okay. Now the distance, the neighborhood, each neighborhood is of radius D, and D is the shortest distance from points of this to L. So we can make sure that, or we are guaranteed that this each neighborhood is inside D. Okay. We can also write also each neighborhood, each nk contained in D. Okay, because their radius is D and D is the shortest distance. Okay. Right. Now, since mod f of z is less than or equal to mod f of z naught, okay, for all z belongs to D, it is true for, because if we want to apply the lemma, what we require? We require that this condition mod f of z is less than or equal to f of z naught in a neighborhood. Okay, so we are considering, we will apply the result for each neighborhood n naught, n1 and so on. Okay, so it is true for n naught, that is mod f of z, or we can write it is true for it is true for each nk. Okay, that means mod f of z is less than or equal to mod f of z naught, okay, for all z belongs to nk, right? So in particular, first in particular, mod f of z is less than or equal to mod f of z naught for all z belongs to nk. That means take k is equal to, first consider this neighborhood n naught, right? Then by the above lemma, what we have proved, the lemma says that whenever you have a constant, this, let's go through this lemma statement, right? If mod f of z is less than or equal to f of z naught, right, then in that neighborhood, right, then what is the possibility is that f of z is constant throughout that neighborhood. Okay, throughout that neighborhood. Okay, so therefore here we have a, by the above lemma, because of n naught this is true, so f of z, this is constant, so this should be equal to f of z naught for all z belongs to n. Now we know that z1, how, because they remember we have to somehow go from z0 to zn, which is p. So how we go via z1 and so on. Z1 belongs to n naught, so therefore f of z is same as, in particular, again in particular, f of z1 is equal to f of z0, since z1 belongs to n naught. Okay. now consider now consider n1, n1, right? So what we have here is mod f of z is less than or equal to mod f of z naught. Okay, that is, but our f of z naught is same as f of z1, so what we have is mod f of z is less than or equal to mod f of z1 for all z belongs to n1, right? This is by again assumption. Only possibility is that f of z1 is equal to f of z naught, right? This implies, again by lemma, so again by lemma, what we get is f of z is equal to f of z1 for all z belongs to n1. Again in particular, because in n1, we know z2 belongs to n1, right? So in particular, this implies f of z2 is equal to f of z1. The reason is z2 belongs to n1, right? So if you combine these things, f of z1 is equal to f of z0 and f of z2 is equal to, therefore f of z2, which is equal to f of z1, and f of z1 is equal to f of z0, right? For n0 and n1 you got this. Now by repeating this process, by repeating this process, we get, what we get is that f of, for last one, that means mod f of z is less than or equal to mod f of z previous one, which is z n, up to what points we have taken, z n minus 1, and then line is z n. Okay, so this is same as z n minus 1, right? This is this is true for all z belongs to this n minus n minus n minus 1. But again, as zn belongs to this one, this implies we get that f of z is equal to f of z n minus 1. Okay. Sorry, this is equal to, sorry, here it is z naught. Okay. Z naught, z naught, okay, for all z belongs to n minus 1. In particular, zn, which is p, is here. Okay, so in particular, f of z n is equal to f of z naught, right? That is, we are getting, this implies f of p, zn is p, which is equal to f of z naught, right? Fine. Okay, so that, therefore what we have shown is that since p is arbitrary, we get that f of z, we get f of z is equal to f of z naught for all z belongs to D. This implies f of z is constant. F of z is constant, which is a contradiction, because our given, we started with an analytic function which is non-constant in domain D. Okay, so this contradiction arises because we have assumed that suppose there is some z naught which achieves maximum of that maximum value in that domain. Okay, so this is not true. Therefore this modulus of f of z, okay, has no maximum value, in this domain D. Okay, so as a corollary, we can understand this result better way. That means we already know that if you take a closed region, okay, so that means suppose f, or f of z, is continuous Suppose f of z is continuous on closed, okay, uh, closed bounded region. What is that? If you take a function, f of z is continuous on closed bounded region R, and f is analytic um, on the interior, okay, on the interior of R, which is a domain in particular, okay, then this f of z has maximum value, on um, the boundary of this R, not inside R, okay. Here we'll write mod f of z, then mod f of z has maximum value in R, okay, which occurs on boundary, okay. Then mod f of z has a maximum value in R which occurs somewhere on the boundary, of R, but not inside R, okay, fine. So what is the proof? Proof is not a difficult one. So proof is that we know this f of z is continuous on a closed and bounded region. So if we know f is continuous on a closed and bounded region, we know it attains its maximum value. Since f of z is continuous on closed bounded region R, uh, there exists m, okay, greater than 0, such that mod f of z is less than or equal to m. That means we know it is it attains its maximum value, okay. And there exists, you can call it, and mod f of z naught is equal to m, okay. So I mean there exists some point in R which happens this, okay. Now also by previous result, since f is analytic, since this f is analytic, okay, f is analytic, uh, we may want to take here f is analytic and non-constant, okay. So if f is analytic here and non-constant and this interior, okay, since f is analytic and non-constant in interior of R, which is a domain, because R is closed and bounded region, so therefore its interior is a domain. So what we get here is that this f of f has no maximum value, in interior of R, okay. But it one way we are saying that it has a maximum value in R, but it has no maximum value in interior of R. This implies here you say that here what I want to say is, whenever I'm writing this, because it is a complex valued function, so we have to say that mod f of z, okay. This implies mod f of z, so this has no maximum value in interior, but one way is that this mod f of z has definitely maximum value in R. That means the maximum value should attain in boundary. That means f of z has maximum value only on the boundary of R, okay. That's why the maximum value for non-constant analytic functions will be at boundary, okay, not inside, right. So this is about maximum modulus principle. Next class we'll see some other properties of analytic function, okay. We'll stop here.